So I want to jump right into the relationship between classes part. So a typical object-oriented program is made up of multiple interacting classes. Right? It's very unusual to have a program that only has one class. Right? And so especially when you have a large program that has many different types of interacting objects, the relationships between those classes becomes important so that you can understand how is this program working. Right? So for example, you might have classes that are built using other classes. Right? So that describes the structure of classes. And you might have classes that interact with other classes. Right? Well, you always have classes that interact with other classes. So that describes the behavior between classes. Right? There are different UML diagrams that describe behavior and describe structure. We don't look at the behavior diagrams in this course. Okay, so we're interested in the structure in this course, right? So how do you make a class that uses other classes? Right? And so you need to talk about the relationship between classes, right? And so the weakest relationship you can have between classes is called dependency, right? So dependency just means that a class uses another class. Right? That's all that it means, right? And so this models the uses relationship. Right? So we say that if a class X uses another class Y, then X depends on Y. There's supposed to be a Y here. Right? Now, it can also be the case that Y depends on X. Right? So you can have a two-way dependency relationship. How do you know if X depends on Y? Well, you just look at the class X and see if Y appears anywhere. Right? So if Y is a field of X, then X depends on Y. Right? If you've got a method that mentions Y, method or constructor that mentions Y, then X depends on Y. Right? So if you go and look at the class object, right? The class big O object, right? And you just scroll through its documentation, right? You see that there's a toString method that mentions the string class, right? So we know that object depends on string, right? We also know that it depends on this class called big C class, right? And that appears to be all of the dependencies that object has, right? So even the class object, which sits at the top of Java's inheritance hierarchy, depends on other classes in the language. Right? If you look at the string class, right, and scroll through, you don't even have to scroll through. If you look at the top, right, you can see right away that the string class needs the object class. Right? So string depends on object. Right? If you scroll through and look at the,
Do all child classes depend on the parent class?
Yes. Yeah. So the relationship between child classes and parent classes is dependency, but it's also stronger than dependency. So we'll look at that in a little bit. And you can see that there's a bunch of other classes that string depends on, right? So it depends on this thing called charset, string buffer, string builder, right? And it also depends on somewhere, object there, right? So it also depends on object because object appears as an argument in the equals method. Right? So for the string and object classes, they have a two-way relationship, right? They depend on each other. So you can show that relationship with a UML class diagram. Right? And so our point2 class depends on the class string, right? So it has a toString method. Right? So it depends on the class string. So the way you show dependency is you write the two classes as a box, right? And then you connect them using a dashed open-ended arrow. So believe it or not, all of the actual, like that dash, the fact that this is dashed is important in UML. The fact that that's an open arrow is important in UML. Right? Point2 also depends on this class called vector2, which we haven't talked about in the course. But it also depends on vector2. So you can show that relationship by drawing a dashed line with an open arrow. Right? Vector2 depends on string because vector2 has a toString method. Yeah?
If there's another dependency of vector2 that point2 didn't depend on,
yeah.
would that still count as a point2 dependence, or do you not?
No. So you don't model, so we're only interested in the direct dependencies. Yeah, but that's a good question. All right, so dependency can also be two-way. So for example, you might go into the vector2 class and modify it somehow so that it also depends on point2, right? So for example, you might have a constructor in vector 2 that takes in 2 points, right? You compute the vector by subtracting the 2 points, right? If you had such a constructor, vector 2 would then depend on point 2, right? So this relationship here can be two-way, right? And you indicate that with 2 separate lines with arrows pointing in the opposite directions. Okay, so that's dependency. So dependency is pretty straightforward, right? If a class uses another class, there's a dependency relationship. Association is a stronger form of dependency, right? So association models HASA, right? And so HASA means that your class X has a field of type Y. Right? So when you look at the fields, if any of those fields are of reference type, you have an association relationship. Right? And like dependency, association can be two-way, right? So if X has an association relationship to Y, Y can have an association relationship to X. Right? Sorry, this is from another class and from a previous year. So there's, in a previous version of this course, there was this class called ranged value and there was a class called range, right? So range is just a mathematical interval, right? So between, say, 0 and 10. A ranged value is a value somewhere in that range, right? So every ranged value object has its own internal range object. And so you can model that as an association relationship, right? An association relationship is shown with a solid line, no arrows, right? If you want to, you can include the multiplicity. So what this diagram is saying is that every ranged object has one has one field whose type is range. This is an example from the standard UML textbook that shows the relationship between a class called show and a class called performer, right? And so this is supposed to be modeling like a Broadway show or something like that, right? There are some names on the diagram. So there's this name orchestra, there's this name cast, there's this name backup, right? So orchestra is the role between, that describes the relationship between a show and a performer, right? So to read this diagram, what this says is that if you look at the line from show going to performer, right? So a show can have any number of performers, right? A performer might belong to any number of shows, as a member of the orchestra, right? So a show might have any number of performers who are in the orchestra. A performer might be a member of the orchestra in any number of shows, right? And similarly, the same is true for cast, right? So a show might have any number of performers who are part of the cast, right? And a performer, might be a cast member in any number of shows, right? And then there's this relationship between between performers, right, in the backup role, right? And so this one's tricky to read. So a performer might be a backup to either 0 or 1 lead actors, is the way you read that. Right. So that's association, right? So association just means that a class has a field that happens to be a reference type. Right. And now we talk about aggregation and composition. So as we're going, the relationships get stronger and stronger and stronger, right? So aggregation and composition are just stronger forms of association, right? The term aggregation is controversial. So not everybody believes this is a proper relationship, right? Okay, so both terms describe HASA, right? So remember that I just said that association is also the HASA relationship, right? So you know that if something is an aggregation or a composition, right, it has fields that are of reference type, right? So for example, a university might have a collection of departments, right? Every department might have a collection of professors, right? So it still has a, right? So at this point, we still don't know if this is association, aggregation, or composition. Well, we know it's association. We don't know if it's a stronger relationship yet. So composition implies ownership, right? So for example, if the university disappears, right? So if Queen's University were to go away for whatever reason, all of its departments also go away, right? You can't have a department that exists without the university, right? So a university is a composition of departments, right? Aggregation does not imply sole ownership, right? So if a department disappears, so for example, suppose they, for whatever reason, we decided to get rid of the School of Computing Science, right? It's not necessarily the case that the professors also disappear, right? In fact, it's almost certainly the case that the professors just go to other departments, right? So a professor can exist without the department, right? A department cannot exist without the university, right? Professors can exist without their home, without a department, right? And so the department is an aggregation of professors. Now, aggregation and composition, the way they differ from association is that they are one-way relationships, right? So association, you can have a two-way relationship. In aggregation and composition, the relationship is strictly one way, right? So something is made up of something else, right? But the opposite, it can't also be true, right? So X can be made up of Y, but Y cannot also be made up of X, right? So if you see aggregation or composition, you can just think made of, right? Or made up of. So imagine that a person has a name and a date of birth, right? You often see the person example in these introductory programming courses. It's not a great example, but it shows up a lot, right? So a person has a name, they have a date of birth, right? So if we look at the code and we look at the constructor, right? You see here that the field name just gets set to the incoming name, right? And the field birth date just gets set to the incoming birth date, right? Notice there's no new string object created here. There's no new date object created here, right? When you return the name, right, you don't return a new string object. You just return a reference, whatever your field is, right? And when you return your birth date, you don't make a new date object. You just return your birth date, right? So that example there is using aggregation, right? So for example, if I was to ask you to implement the person class, and provide a constructor and a get name and a get birth date method. At this point in the course, that's the code you would probably write, right? These fields are of reference type, but you're treating them like they are primitive values, right? This name equals name, this birth date equals birth date, right? Return this name, return this birth date. So no new objects are being created, right? So notice that that constructor doesn't make a new copy of the name and birth date objects that it was passed. Right? So it's not making a new copy, right? That means it doesn't own, right? Whatever name this thing, whatever string this thing is pointing to, and whatever birth date this thing is pointing to, the person object doesn't actually own that object, right? Somebody else has a reference to that object. Someone else has a reference to that object, right? And so the person object can't possibly own the name or date object. The string or date objects corresponding to the name and birth date, right? So the name and birth date objects, they're being shared by whoever called that constructor, right? So both the caller and the person object are holding references to the same objects, right? So for example, the caller makes a string and they make a date. Date's weird. So that's the date 1991, March is the month number 2, and that's the 26th day, right? This is an actual class in the Java standard library, right? If someone makes a person object using that string and that date, this is the following picture in memory, right? So the caller has a string and a date object, right? So that string is just that string object there, right? That date object is just that date object there. The person object, it has a field called name, but that field just points to that string object there, right? So caller has a reference to that string object. The person object has a reference to that string object. No one actually owns that object, right? It's shared ownership here, right? Similarly with the date, right? That date, points to that object there. That date points to that object there. No one actually owns the date. So this is aggregation, right? It's aggregation because, right? Because a string does not have a reference to a person and a date does not have a reference to a person, right? The relationship here is strictly one way, right? Person has a reference to a string, person has a reference to a date. String does not have a reference to a person, date does not have a reference to a person. Relationship is strictly one way, right? So this is aggregation. Okay, so in aggregation, right, no one owns that date object. So if that date object was to change for some reason, both the whoever has a reference to that date object will see the change. That means the person's birth date can change, right? So for example, the caller has a name, Billy Bob. They have a date, March 26, 1990. Then they make a person object using that string and date, right? If the caller changes the date object, changes the state of the date object, right? So they now change the date to November 3rd, 1995, right? If you ask the person what is their birth date, it's now November 3rd, 1995, right? So the person object doesn't control its own birth date, right? Somebody else can change the birth date of the object without asking the person object itself, right? Which might be strange, which you might think is strange, but that's simply the consequence of using aggregation. Right? So because that date instance is shared by the caller and the person object, right, the caller can modify the date, right, and the person object now sees a changed birth date. Similarly, the person object can change the birth date, and now the caller sees a modified date. Right? So nobody actually owns the birth date object. Now notice the string object, the name, right? That's being shared by both the person and the caller, right? But neither the caller nor the person object can actually modify the string, right? Because the string's immutable, right? So immutable objects make very good building blocks for other objects, right? Because their state never changes, you don't really care about ownership anymore, right? You can freely share that object, no one can change it, so you never have to worry that its state has changed on you, right? And so that's one of the big benefits of using immutable objects, right? It makes your code much easier to write, it makes it much easier to maintain, and it makes it much easier to debug. But they're not always feasible to use, right? Often you want an object whose state can change. Right? So to show an aggregation relationship, the picture looks slightly different than association, right? It's still a solid line, right? But now the whole object, so person is the aggregation, right? It gets diamonds attached to it, right? So open diamond on the person object and a solid line connected to date says that person is an aggregation of one date object, right? And person is an aggregation of one string object. Right? So the diamond goes on the whole object, right? No diamonds go on the quote-unquote part objects, right? The objects that the whole is made up of. All right. I guess that's a good place to stop. And so the next lecture I'll tell you about composition, and composition greatly complicates your life. So you have to be careful to make sure that you do a whole bunch of things when you're implementing a composition.